Hello, my name is Chris Harris and I'm from Allery Chemistry, and this video is for the CIE, so that's the Cambridge International's Topic 3 chemical bonding topic. So this topic is going to go through obviously different types of bonds, so covalent, ionic, metallic, and there's also some quite tough stuff in here to do with hybridization and orbitals and things like that. So there's quite a bit of stuff in here. So this is really designed to talk through or kind of work through them different I suppose bits of content in topic 3. Now this is obviously a PowerPoint slide. They are available to purchase through my test shop. If you click on the link in the description box below, you'll be able to get a hold of them there. They're great for revision. They're actually bundled up as part of the the physical chemistry topic with other topics as well, but it'll be clear. If you go and have a look on there, you can see them. Great for revision and on the move, etc., and using alongside your revision books and notes and whatever you have there. So hopefully these should be nice and straightforward, nice and clear. So again, it's designed specifically for the CIE topic, so hopefully everything on here should be nice and clear. So let's start with bonding first, so ionic bonding first, should I say. Now, some of this stuff you might have seen from GCSE. Some of the stuff you'll see, particularly with the orbitals bit and energy levels, is kind of derived from topics 1 and 2. So you'll find a lot of the topics in CIE kind of merged together. So I will be kind of reflecting back on them topics as well. It's really important that if you haven't seen them videos or you're not really comfortable with some of them areas, I can't emphasize enough that you should be comfortable and familiar with them at least to kind of get some of the concepts here. I'll try and bridge it as much as I can, but it's just to kind of make you aware of it. So let's start with ionic bonding first. So obviously bonding is quite an important part of chemistry because it's how atoms and ions join together, and it's how we create molecules, and obviously that's just fundamental to chemistry. So one of them is obviously ionic bonding. And ions, as you've seen earlier in topic 2, ions are oppositely charged. So ions are charged particles, but ionic bonding is where you've got oppositely charged ionic substances or ionic entities, should I say, and these are held together by electrostatic attractions. Okay, so electrostatic meaning obviously electro meaning kind of charged, static meaning they're not moving, and attraction is obviously where they kind of attract together. That's really all it means. They always give these kind of fancy names in chemistry. So let's have a look at the first one. This is sodium and chlorine. So these are two atoms here, and we know they're atoms because this is just showing the valent electrons. So these are electrons in the outer shell. So obviously we know that sodium's in group 1, so it has 1 electron in its outer shell, and chlorine is in group 7, so it has 7 in the outer shell. Now, you'll probably recall, I think from topic 2, that in order for these to, and topic 1, there's a little bit in topic 1 as well, in order for these to form ions, then chlorine needs to accept an electron and sodium needs to lose an electron, and effectively they form charged particles. So there we are. Okay, so sodium forms a plus charge and chlorine is minus. And when we draw these diagrams, these are called dot cross diagrams, by the way, and you'll see them in covalent bonding later on. But effectively, the positive and negatives, they effectively attract to each other. So just as a reminder of the other ions that can be formed, so obviously this is in relation to the common ions in groups 1, 2, 3, 5, 6, and 7. Obviously the kind of the ones right at the end don't form any ions. They're your noble gases, so they already have a full shell of electrons. And this group in the middle, your transition elements, these ones, or D block elements, should we say. So these ones can have variable, well, transition elements can anyway. These can have variable charges. They can form variable ions, so they don't really form the same kind of pattern what we see there. So, we need to know some molecular ions as well. And again, you would have seen these in topic 2, but just to kind of bring some of them back in. Hydroxides, OH-, you need to be familiar with these. NO3 minus is nitrate ions, ammonium is NH4 plus, sulfate ions SO42 minus, carbonate ions CO3 2 minus. You might see hydrogen carbonate as well, which is HCO3 minus. So you might see various different molecular ions. You do need to be familiar with these because you will see compounds and substances with these ions that exist. Okay, so we can work out the formula actually of a compound by using what I like to call a swap and drop method. Now you might have your own methods and you might be able to work this out without using this method. It's just a way in which you can work something out, and you might have your own, which is fine. So you go with whatever you feel comfortable with. But I'm going to show you this method because it may help some people. So working out the formula of substances is quite important. Obviously, it's an integral part of chemistry. So in this case, we're going to show you this method here. So we're going to look at calcium and nitrate ions, for example, so NO3 minus and Ca2 plus. Now, if we wanted to know what is the formula of calcium nitrate, this is the way in which we go about it. So, or you could go about it, should I say. So what we do is write out the charges first, write out the ions, and then we do a swap of the charges. So we basically move the 2 plus over to the NO3 and remove the minus bit from the NO3 over to the calcium bit, as you can see there. And then we drop the charges. So we basically drop them so they're kind of subscripts. Now you'll notice that with the calcium, we don't bother putting the 1 there. We just kind of omit that because we know just 1 there, and then the 2 is there. Notice what we do with the NO3 though is that we have to put that in brackets to basically say, right, we've got an NO3 kind of unit and we have 2 NO3s. That's why we put the brackets around there. We can't just put 2 next to the 3, otherwise it look as though we've got 32 oxygens, which just doesn't happen. So yeah, very important to put your brackets around that as well. And we simplify to the whole number ratio if it's possible and if needed. In this case, it's already in its simplest form, and so therefore we have formed our substance, which is calcium nitrate. So that's the formula for calcium nitrate. Let's look at another one. Let's look at calcium and oxygen. Follow the same method. Swap the charges over, 2 minus and 2 plus. Drop the charges, Ca2 and O2, so take the little negatives and positives away. And then in this case, we do need to simplify it to its whole number ratio, which is going to be, or the kind of lowest, the lowest common denominator, I suppose. In which case, this is CaO, so that's calcium oxide. Okay, so that's the formula for calcium oxide there. So what we also need to be aware of is what is an actual ionic structure. And a common one, I suppose, is sodium chloride. And there's many examples of this, but ionic substances are generally form these giant structures. And giant meaning exactly what it is. They're big. They're very large structures. Now, ions, obviously, the ionic bond itself is the attraction between oppositely charged particles. So it's the electrostatic attraction. And these two here are examples of ionic bonding. Now, when we write them just as CaO, and it looks as though it kind of floats around on its own, just as a pair, quite nicely. In reality, that just isn't the case. These atoms want to be surrounded by oppositely charged particles, and they will arrange themselves, as long as it's feasible, they'll arrange themselves to be next door to as many different oppositely charged particles as they possibly can. And this is where you get these giant structures, and this is why it's important to kind of understand this. So if we look at sodium chloride, an example, which is table salt, effectively, you can see on this is an example of a giant ionic structure. You can see in this example it's cube-shaped, and the purple spheres represent Cl- ions, and the yellow spheres represent sodium ions. But you can see from the structure, you have this regular kind of pattern of different ions that stack together. This is cubic in shape, and you have this giant repeating pattern. And if you notice, if you look carefully at some of them, you'll see that the sodium ion is trying, and with the chloride ion as well, is trying to be next door to as many opposites as it possibly can. and this gives it this incredible robustness. It's this really, the kind of physical properties of it kind of stack up. So effectively, they are soluble in water. So if you take salt, for example, this is just salt, and you put that into water, it will break down in water because each one of these has an ion. So you've got a negative and a positive charge kind of stacked up here. When you put it into water, water is polar, as you'll see in a moment. And effectively, it starts to pull this structure apart. And we can see evidence of that because we see salt dissolves in water. However, they also do conduct electricity when they're molten or when they're dissolved in solution as well. So if we take salt water, for example, it will conduct electricity because you've got ions that are free to move around in solution, and that's quite an important aspect of something being able to conduct electricity. Same if it's molten as well. So if we melt salt, which I'll come back to in a moment, then the ions are free to move around as well, and so therefore it will also conduct electricity. So it's quite a common feature. But as I mentioned before, this kind of really kind of robust structure has a high melting point. There are lots of strong electrostatic forces between oppositely charged ions. Okay, so in other words, sodium is next door to loads of different chloride ions. Each one of them ions there's an attraction between them. But if it's surrounded by loads of these ions, that's a lot of force to break down to actually melt this. So salts are actually really difficult to melt. They've got incredibly high melting points. And table salt, for example, if you put that in a frying pan on a high heat, it's unlikely to melt because of the strong electrostatic forces. However, if you put it in water, it will break down quite readily. So it just shows you the power of these forces, I suppose, between molecules. In this case, is probably more powerful than the thermal energy required to melt it. So it's quite strange, quite quite an unusual concept. So they are brittle, though. Obviously, we know salt. If you take a clump of salt and then push it with your thumb, it'll probably break. So it is that the layers do kind of slide around quite a lot. If you hit it, and if you get two negatives together, so a chloride and a chloride, obviously they repel, and so therefore it breaks. So they are quite negative, they are quite brittle. So ionic compounds generally. Okay. So another way to kind of just prove for charged particles, you might see this in your practicals, you might not. It's just a way in which you can demonstrate ionic substances. So in this case, we're going to use a process called electrolysis, which again you might have seen at GCSE, and we're going to use copper. In this case, we're going to use copper 2 chromate on wet filter paper. The reason why we do this is because copper 2 chromate is coloured and it's green. So what we do is we basically put a drop of green copper 2 chromate on wet filter paper, and we pass electricity through it. And effectively what we're doing is pulling the charges apart. Now, you can apply this, and you know that copper 2, again from topic 2, the Roman numerals tell us that copper is a 2+ charge, and obviously the chromate is 6 minus, which is here. So that's your chromate. Now, when we switch the electricity on, hey presto, your copper 2 ions move towards the negative side, and copper 2 is blue, so you get this lovely blue colour that appears on there. Then if you look on the other side, your chromate ions are negative, and so they move towards the anode, the positive side of it, and you get this yellow solution. So this is just, this example here, copper 2 chromate is used deliberately because it forms coloured substances. So obviously it's green to start with, and you get blue and yellow either side. Other ionic compounds aren't as colourful, so therefore you wouldn't see it, it's invisible. It's just a neat way in which you can demonstrate that you do have an ionic compound, that's all. Okay. Alright, so let's look at another type of bonding, which is covalent bonding. Now, covalent bonding is a different type of bonding. So ionic bonding is where you've got ions, and effectively you have charged particles, and it's an attraction of the charged particles, and that's how it works. Covalent bonding means, to kind of break it down, co means to share, and valent means the outer electrons. So we're sharing the outer electrons in this type of bonding. There's loads of different examples here, and these are probably some of the more common ones. You will see a few more as well, but as you can see, there's quite a few on here, and I think you'll probably get the idea when I talk through them. But like I say, covalent bonding is the sharing of outer electrons in order to obtain a full shell of electrons. So this is a very similar concept to ionic bonding, because they were giving up and accepting electrons to get a full shell. This is the same concept, they're just doing it in a different way. And generally, covalent bonding happens between two non-metals, whereas ionic bonding happens between metals and non-metals generally. So that's as a to give you an idea of which one's covalent and which ones aren't. So your covalent bonds, as you can see, all these are non-metals trying to bond together. Now, in this case, there still is an electrostatic attraction, just like what you had with ionic bonding, except the attraction is not between ions, it's between the electrons that are being shared in the actual substances, I suppose, so a bit like this here. So these are shared electrons in the middle, and the nucleus of the atom in the middle. So it's this kind of attractive force between the nucleus and these shared electrons that effectively create the bond. So we have single, double, and triple covalent bonds, and obviously you've got more electrons are being shared in the triple bonds than they are in the single bonds. So your triple bonds are going to be stronger than your single bonds, and you'll need to know a little bit more. We'll come on to the hybridization and orbitals bit later. That gets a bit complicated there, but for this purpose, it's just basically looking at what a bond is, what a covalent bond is. Now, covalent bonds, these can be represented by lines, as you can see in this diagram. You might have seen these before. And the line represents a single bond, a double line represents a double bond, and a triple line represents a triple bond. So, you've got another type of bond as well, and they've got two names for this. They're either called dative covalent or coordinate bonds, and this is an unusual bond. It's not as strong as a traditional covalent bond, generally. But this is where you have one atom that donates both electrons to another atom or ion to form a bond. Okay, so an example you can probably see on the diagram here is ammonia, which is NH3, which you can see here. So you have your traditional covalent bonds between the nitrogen and the hydrogen atoms, but you have this kind of lone pair of electrons on the nitrogen, and we have this hydrogen ion here that doesn't have any electrons of its own. Its electrons being removed, and that's why it's got a positive charge. So if we then move that across there we are. This is a dative covalent bond. Okay, and the dot cross diagram just illustrates that a little bit clearer, because we know that these electrons have come from the same atom, which case is nitrogen. This is an example of a coordinate bond, or dative covalent, and it's represented with an arrow like that. So if you had to draw this out as a diagram, as you can see there, you've got your nitrogen with your 3 bonds either side, and you've got this arrow here which represents the electrons are moving from the nitrogen, or the electrons are part of nitrogen atom, and they're being donated to hydrogen in a shared way, and we call that a coordinate bond. Okay, so effectively you form NH4 plus, and that's an ammonium ion, which you will have seen in topic 2. Okay, so CO, this is another one. This is carbon monoxide. It has a double bond and a covalent bond. A double covalent bond and a dative covalent or coordinate bond. So carbon monoxide, which is that poisonous gas. It's odorless. You can't see it. It's toxic, obviously. This is obviously the bonds here. You can have a mixture of the two. So you can have a double bond and a coordinate bond in the same. And this is an example of it, which is carbon monoxide. Okay, so let's look at another example. And so this is the one where you've got a mixture of different bonds here. So this is an example of basically aluminium chloride. So you've got AlCl3, but the two molecules are kind of joining together and forming a coordinate bond between the two. So this one's aluminium chloride, and actually the formula of aluminium chloride is Al2Cl6, because this is the most stable form that it exists in. So it's not AlCl3, but it's just really here just to show you another example of that. Okay, so let's have a look, let's kind of dig a little bit deeper into kind of covalent bonding and what this kind of forces, these electrostatic forces are. So here we've got a diagram here, and we've got a nucleus in the middle, as you can see here, and we've got our electrons here. We've got this covalent bond that we've just seen before. Now, you remember that the bond enthalpy, so the strength of a bond, is linked to how long that bond is, and the length of the bond is dictated by the forces that are involved between the nucleus and the shared electrons, as you can see here. So basically, the shorter the bond, the higher the bond enthalpy. Okay, so we need to know this relationship between the two. So in covalent molecules, there are forces of attraction. There we are, and you can see them on there, between the positive nuclei and the negative electrons being shared. So there's your attractive forces here. And it's this that effectively just pulls these two atoms together, and that's effectively what the bond is. We then have repulsive forces as well between the two positive nuclei. Obviously, the nuclei of the two atoms don't want to be near each other, but we also have it between the electrons. The electrons don't want to be near each other as well. So you've got these two forces at play here. So you've got some which helps to pull the atoms together, but not too close, because there's constituents in the atom, that also repel it, that kind of push it away. So there's a balance between the two forces, and as a result, we get something. We get a bond length. We get a distance between. A distance in the bond, actually, so the total length of that. So the greater the electron density between the atoms, okay, so the stronger the attractive force, and so this means that the atoms are pulled in further towards each other, and this leads to a shorter bond and a higher bond enthalpy. So if we've got really strong attractive forces, in other words, the distance between the shared electrons, this electron density here, and the nucleus is quite short, then clearly we're going to have a very strong force here, which is going to pull them closer together and shorten that bond, which makes the bond stronger overall. And we can look at this in terms of your single, double, and triple bonds. And high electron density is shared effectively between them, and shorter bonds, as we go down here, we get a shorter bond and a higher bond enthalpy. So your triple bond is shorter than a single bond, and a double bond is longer than a single bond, etc., etc. So and the reason why is because this density is shared between them, and this will become a little bit more kind of apparent when we look at orbitals. Right, so we need to know, we need to know some shapes of molecules as well, and we need to know some of the rules associated with the shapes of molecules. So let's have a look. So the number of bond pairs and lone pairs of electrons will dictate what the shape of the molecule is, and you need to be familiar with the names of these. Okay, so molecules, they have a specific shape with specific angles, and this is because bonds actually repel each other equally. So remember, when we're looking at bond repulsion of electrons, etc., it's a similar type of concept. So remember, in a bond, you have shared electrons, and electrons in that sharing kind of mechanism don't want to be near other shared electrons. They want to try and repel themselves as much as they possibly can, and that basically gives rise to a shape, particularly if you've got a molecule here where you've got multiple different bonds here. So each one of these has a shared pair of electrons, but they're going to try and repel each other in a three-dimensional space. Okay, so a lone pair next to a bond pair, these repel more than two bond pairs together. Okay, and two lone pairs together repel even further. So if you have a molecule that has a lone pair of electrons, a bit like the example when we looked at ammonia before, which is NH3, that had a lone pair of electrons on there, and it had three bond pairs. So it had three NH bonds and had the lone pair on the top. So that lone pair has a much bigger repulsive force than between two bonds that are next to each other. You'll see some examples in a moment. I'll try and explain that. So there's your ammonia. There it is, actually. There's your example. So there's ammonia. It could be ammonia. So your nitrogen in the middle, and then you've obviously got your bond pairs there as well. Okay. Okay, and there's another one which is water. So this could be oxygen with two hydrogens, for example. It has two lone pairs of electrons, and that pulls that further apart. Now you'll notice that we've actually got some bond angles here. Now this is you'll see in a moment, we call this tetrahedral. So there's a tetrahedral shape, which has a bond angle of 109.5 degrees. Very important to not miss out the 0.5. So basically that's the distance between each one of the bonds in a three-dimensional space. And the wedge basically shows the bond coming towards you, and the dotted line is the bond going away from you. This, obviously, with the lone pair, squeezes that a little bit further, so the bond angle is a bit tighter between these bonds here, which is 107, because remember, this repels this a little bit more, and obviously the two lone pairs repels it even further, and it squashes these two bonds a little bit tighter together, and we get 104.5. So basically, you do need to be aware of these bond angles. Now, you'll notice there's a bit of a pattern here. And effectively, the lone pairs change the shape and the bond angles, as you can see here, and it pushes them closer. Now, generally, for every lone pair that we have, we reduce the kind of bond angles, so the remaining angle between bonds, by 2.5 degrees. So that's generally, you'll see some examples where it doesn't quite happen, but in this example, you can see if we take 2.5 degrees off 109.5, we get 107. And then another 2.5 degrees brings it down to 104.5. We'll go through some of the other examples later on. Okay, so let's look at some actual shapes and look at some specific examples. So when you're trying to work out what shape your compound has or your substance has, you've got to follow a specific method. Now, again, you might have a different method to what I'm going to use here, but this is just a way in which you can do it. So what I would do is I would draw a dot cross diagram out to work out how many bond pairs we have and how many lone pairs we have. So here I've got methane, which is CH4, and you can see we've got 4 bond pairs and no lone pairs in this example. And then with ions, if we have ions, we just add electrons to the central atom for negative ions and remove them for positive ions. So for example, for NH4+, so ammonium, nitrogen would have 4 electrons, all involved in bonding, and so therefore would be tetrahedral. Okay, and you'll see some examples later. So in this example here, we have 4 bond pairs, as we said there. We don't have any lone pairs, so the total is 4. And the total tells you the shape. In this case, it is tetrahedral. If we had lone pairs here, you would need to replace the bonds for lone pairs and change the shape of the bond angle, as we've just seen before. So when we showed you them 3 different diagrams, obviously a lone pair generally reduces the bond angle by 2.5 degrees for every lone pair that you've got. Okay, so here's another example here. This is water, and you can see we've got our lone pair there. So this has got 2 bond pairs, 2 lone pairs, and that means we've got a total of 4. So we're starting from a tetrahedral position. There we are. Okay, so it's based on a tetrahedral position because we have a total of 4. That's the kind of start position. But we reduced the bond angle by 5 degrees because we've got 2 lots of lone pairs in there. So what that means is that we basically see a different structure. We don't have something that's tetrahedral. We have something that's called non-linear, which sounds very exciting, or bent. We call it a bent molecule. So basically any molecule which it was based on tetrahedral and has 2 lone pairs, then that's where it is. So the purpose of this really is to give us a start point. So when we got 2 bond pairs, 2 lone pairs, this gives us a starting position, and then we can alter according to the number of lone pairs. Okay, so let's have a look at some specific shapes then. Let's have a look at some examples. Now, you really do need to be familiar with these, okay? So hopefully this should make it a bit clearer. So we're going to use the number of bond pairs and lone pairs, as we've just seen before, to work out the shape of the molecule. Okay, so let's have a look. Let's have a look at the first one. So we've got a molecule with 2 bond pairs and no lone pairs is called linear. Okay, now all these examples here are not going to have any lone pairs of electrons, so this just gives you an idea. So an example would be beryllium chloride, so BeCl2. So another example, and hopefully you'll probably see the kind of format here, we're going to go in order. So this one's got 3 bond pairs, no lone pairs. All of these don't have any lone pairs on them. Example is BF3. This is what we call a trigonal planar molecule, and the bond angle is 120 degrees, so planar because it's flat. So that's the furthest away these atoms can be, within this molecule. 4 bond pairs and no lone pairs is called tetrahedral, as we've seen before, and that has a bond angle of 109.5. Really important you remember the 109.5. Don't just put 109 down, and that's called tetrahedral. 5 bond pairs and no lone pairs is called trigonal bipyramidal. Looks a bit odd. So effectively an example is phosphorus pentachloride, which is PCl5. So just to kind of pause on this one a little bit, just to kind of show you the shape. So imagine you've got these 3 here, these 3 atoms here. These are all in like a trigonal planar arrangement, very similar to that. We've just tipped it on its side. Okay, so we've got these 3 here, and then up and down, so in the polar, kind of the poles of it, we've got the kind of 2 more atoms here. The reason why it's called trigonal bipyramidal is the trigonal is the triangle bit in the middle here. So if you imagine you draw a triangle. And bipyramidal is because if we join lines up, imagine if we could draw a line from each one of these upwards, you would form a pyramid on the top there, and the same on the bottom as well. So that's why we call it bipyramidal. So you've got 2 pyramids and from a trigonal base, you see. This one has 2 bond angles, 120 degrees obviously between these, which is just the same as that basically. And obviously the difference here is 90 degrees because that's like T-shaped, like a T-shaped molecule. Okay. Okay, so the last one on here, so these are all molecules with no lone pairs, is 6 bond pairs and no lone pairs. This would be something like SF6, for example, and this is called octahedral. The bond angles are 90 degrees between all of them. Now, with octahedral, the reason why it's octahedral is, again, if we draw a line going 1, 2, 3, 4, up to these, we've got the square in the middle, and then you've got the 2 poles either side, then it would form an 8-sided 3-dimensional shape. So you would have 1, 2, 3, 4. So there's your different kind of faces. Imagine you have to be a little bit more visual here. It might be quite tricky. Some of you might be able to see this. Some of you might be quite tricky. But that's why it's octahedral. Don't get that confused with the fact that it's got 6 bond pairs for something that's octahedral. Octa is obviously 8, but it's just the shape. If you had to draw that into a 3D shape, you'd have 8 faces on it. Okay. Right, you must remember them. That's really important. Right, so we're now going to look at some examples with lone pairs this time. Okay, so let's have a look at this one then. So this is 3 bond pairs and 1 lone pair of electrons. This is classed as pyramidal, so NH3 is a classic example of this. And remember, you have a lone pair of electrons. This was based on, so you've got 1, 2, 3, 4, so you've got 4 in total. So it's based on a tetrahedral, but it's got the lone pair in there. So we reduce the 109.5 by 2.5 degrees to give us our bond angle of 107. Okay, so that's total bond and lone pairs is 4. So that's our starting point, but the lone pair obviously squeezes that a little bit further. Okay, something with 2 bond pairs and 2 lone pairs is H2O, and it's bent or nonlinear, as it's also known as. Again, the extra lone pair of electrons creates 104.5 degrees. Another example, so 3 bond pairs and 2 lone pairs. An example is ClF3, okay, and this is trigonal planar. So we've seen that one already. We've seen that one, in the previous examples. There's no difference here. This one is slightly different in the fact that it has 3 bond pairs and 2 lone pairs. So it's not just 3 bond pairs. It does have these 2 extra electrons. But this is where that rule breaks down. Remember when I said that for every lone pair of electrons that you have, you reduce the bond angle by 2.5 degrees? This here is one of the exceptions. So in this case, you still do have your 3 bond pairs, as you can see on here. So there's your 1, 2, 3. But the 2 lone pairs of electrons kind of sit top and bottom. And what they do is these electrons here will squeeze these ones down, but these electrons here will squeeze them back up again. So effectively they cancel each other out and you end up with trigonal planar, which is what you've seen before. So the bond angle remains the same at 120 degrees. Okay. Right. So, and the last example here is 4 bond pairs and 2 lone pairs, and this is square planar. So, for example, xenon tetrafluorides, XEF4, it has 2 lone pairs. Again, a similar principle to the trigonal planar. You have a square in the middle here, each at 90 degrees, and the lone pairs cancel each other out. So these ones will squeeze these bonds down, these ones will squeeze them upwards, but they cancel out, so you get this nice square shape. Okay, so the bond angle, like I say, it remains unchanged. Like I say, they kind of repel equally from both of them. Okay, right, so make sure you're aware of them bond angles. Make sure you kind of know what they mean. You've got to remember them. I know there's a lot to remember here. A lot of the time, it's going to be practice. You must keep practicing. Okay, so giant covalent structures. So these are effectively, obviously, we looked at covalent structures just before then. Some of them were what we call simple covalent. So they were very just small molecules. But you can get giant covalent structures, a bit like what you had with giant ionic as well. So, giant covalent structures, some classic examples include graphite and diamond. So if we start with graphite first, so obviously graphite is found in pencils. So it's not lead that's found in pencils, it's obviously graphite. Each carbon is bonded 3 times, and the 4th electron is what we call delocalized. So it's not actually attached to any, it's not bonded to anything in particular. You might have seen some of this before, probably. So graphite has loads of strong covalent bonds between the carbon atoms, so it has a really high melting point. You know, if you try and melt graphite, say from a pencil, it doesn't melt very well whatsoever. Now, they do have these delocalized electrons, and they kind of sit between these layers of carbon atoms which sit in rings. Now, these layers are held together by weak forces. It's them delocalized electrons which create that weak forces. And that means actually the layers slide quite well over each other. So, very useful obviously for a pencil, because when you put the graphite against paper, what you want is shards of graphite falling off the pencil and going onto the paper. That's the whole point of a pencil. So it's just as well that these layers are quite slippery and, you know, it can kind of slide off quite readily. Also, these delocalized electrons between the layers, they actually allow graphite to conduct electricity. So they're a really good conductor of electricity. And quite lightweight as well, actually. So, you know, you can see quite a lot of good uses for it. And the layers are quite far apart in comparison to a covalent bond, and this means that graphite has a low density. So it's not a dense material by a long shot. Say when we look at diamond, for example, which is the next example. So it's quite low density, and it is insoluble as well. It doesn't dissolve. The covalent bonds are far too strong for water to break them apart. So it's not like ionic compounds where generally ionic compounds are quite soluble. You know, water can break the ion structure down. It's not the case with graphite. Okay, so let's look at diamond then. So diamond is giant covalent as well. This time, again, it's made from the same material, same atom, which is carbon, but the structure of it, the way in which these carbon atoms are bonded to each other is different. In this case, it bonds 4 times in a tetrahedral shape, and obviously you've seen tetrahedral before, just before when we looked at the bond angles, or the shapes of the molecules. They're tightly packed, rigid arrangement allows heat to conduct well in diamonds, so they're pretty useful. They're used in like circular saws and drill bits and bits like that in the construction industry. Obviously, when they're used to cut stone and brickwork, they can get hot quite readily. And what you don't want is the blades to start melting or kind of warping. That could be quite dangerous. So they usually put diamonds on them to toughen the material up. So it means it can take the heat if it's been used to cut something. And unlike graphite, diamond can be cut to make gemstones. So obviously you've seen diamond jewelry, for example, really expensive metal. Really expensive mineral, sorry, not metal. Definitely not a metal, by the way. Carbon is definitely a non-metal. It's got a very high melting point, loads of strong covalent bonds, okay, and it also makes it quite hard as well. As I mentioned, it's used in cutting materials. Diamond, it doesn't conduct electricity. It doesn't have delocalized electrons like graphite does. They're all occupied in bonding. And diamond is insoluble as well, so obviously it doesn't dissolve the covalent bonds, just like what they are in graphite. They're just far too strong to actually break apart and dissolve in water. Okay, so another example is silicon dioxide. This is sand, effectively, so SiO2. It has a very similar structure to diamond. So if you might see in the exam, they might talk about silicon dioxide. That has a similar structure to diamond as well, the same properties. So makes it quite easy to try and remember what's going on. Right, so still sticking with covalent bonds. This is where we're going to look into a little bit more detail. And I would say, out of all of this topic, this is going to be the most trickiest and demanding part. So I'm going to try and talk through it in as clearly as I possibly can. But if you're sitting there thinking this looks really difficult, it's because it is. Okay, that's not to frighten you. It's just to kind of think, well, actually, okay, you should be finding this quite tricky. Hopefully, if you understand what's going on here, it makes it a little bit easier, hopefully. Okay, so here we go. Right, so we all have to learn somewhere. So I had to learn this as well. When I was many years ago, when I was at school or even university or anything like that. So we all have to pick this up. So hopefully it should be nice and straightforward. Fingers crossed. So anyway, when we looked at covalent bonds, we've seen single bonds and double bonds and triple bonds. And we've seen in topic 2 where we looked at orbitals. And remember, we had different types of orbitals. You had s orbitals, you had p orbitals, d orbitals, and f orbitals. You had all these different orbitals. And if you remember from topic 2, the s orbitals were spherical, so they were round, and p orbitals were they look like 8s, like a number of 8s, figures of 8. And you had 3 different types of p orbital. You had px, py, and pz. So you've got 3 different types there, and you only have 1 type of s orbital. Okay, so if you can recall that from topic 2, if you're not too sure on that, I would urge you at this point to just go back and look at that, because I'm going to be kind of talking about this in a bit more detail, building on that knowledge. Now, bonding is when these orbitals overlap. Okay, so they start to merge together, and as chemists do, they give them fancy names, and they use the Greek alphabet quite a lot to do this. So you have what you call sigma bonds and pi bonds, and these are bonds that are involved in covalent bonding. Okay, so they overlap and they form this covalent bond, as we've seen here before. So, like I say, from topic 2, I urge you to have a look at that first if you're not sure what I'm talking about here. Okay, I will try and bridge it the best way I can, but obviously it would help if you know this bit. So you've got 2s and 2p are quite close in energy. Okay, now on the diagrams in topic 2, you'll see we drew energy diagrams, and we showed the s orbitals and the p orbitals, and we drew kind of them in order of energy. Now the s and the p are quite close in energy, and that gives this kind of unique feature in terms of what they can do for bonding. So given the right amount of energy, this allows electrons to move from the 2s to empty 2p orbitals quite easily. So it's a bit like, I'm going to use an analogy, it's a bit like a double-decker bus. Okay, so you've got people sitting on the bottom layer and people sitting on the top layer. Now, it doesn't really take that much effort to go from downstairs to upstairs in a bus. And if you wanted to go upstairs, you could do. But in theory, if you really didn't want to expend that much energy, you'd just sit downstairs, wouldn't you? So it's kind of the same. See orbitals in a similar way. You've got the s orbital, which is like the downstairs bit of the bus, and the p orbitals, which are upstairs. And there's some empty chairs upstairs, and we can move an electron or a person from downstairs to upstairs in a free seat if we wanted to. Okay, so, and see it in this way. So this is like energy, I suppose, the energy difference. So here, what we're going to do in this example is we're going to be using, use bonding with carbon atoms. And for bonding, for bonding to occur, covalent bonding to occur, we must have singly occupied orbitals. Okay, that's really important. So in other words, if we use that bus analogy again, in order for a bond to occur in an atom, there must be a free seat upstairs, okay, with nobody sitting in it at all. So it's the same with this. So in order for something to happen, you must have a singly occupied orbital, okay? So actually, if I use that's probably not a good example. Let's say if you want to this might be a bit weird. I don't mean it to be weird at all, but if you have, say, a bond between two passengers, say, and you want them passengers to maybe have a conversation with each other, you've got to have a spare seat, haven't you? So one person might sit on the seat, and they might have a spare one, on the next to you, nobody sitting next to you. Let's say the bus stops at the next stop, it picks some people up. That person then comes onto the bus and sits next to you. Now, for that person to have a conversation with you, they need to realistically be sitting next to you, don't they? So they need to have a free space next to you to do that. Otherwise, they'll be shouting across the other side of the bus. Now, in reality, does that happen? I don't know. Most people probably don't. They just keep themselves to themselves, don't they? But in atoms, it's exactly the same. So in other words, for two atoms to kind of bond together, they've got to have a singly occupied orbital. You can't have it where, it's fully occupied. Okay, and it must be singly occupied. I hope you get that so far. So there are two ways in which a CH bond can be formed. And here I'm just going to kind of talk through the two main ways, but there's obviously one way in which it does actually kind of form, and that's what I want to talk about here. So we can either overlap the two p orbitals with the s orbital in hydrogen. So we're going to form a CH bond. So remember, in hydrogen, you only have a 1s orbital because it only has one electron in there, so it's singly occupied. And with your carbon, you have 6 electrons, obviously, in total with carbon. So you have some in the p orbital as well. So you can overlap the two p orbitals with the s orbital in hydrogen, and there we are, you formed a bond. Or you could be quite clever, and you can migrate an electron from the 2s orbital, that's a bit like downstairs in the bus, into one of the empty 2p orbitals, and we form a brand new orbital called a hybrid sp3 orbital. Wow, okay, right, let me just kind of pause there and just explain what this means. So, hybrid, you might have seen cars which are hybrid cars, okay? So, cars are either petrol or diesel, so they fossil fuel run, or they're electric. And then you can have a car that kind of sits in between the two and has a bit of petrol and a bit of electric in it. And we call that a hybrid. So basically it's a merger of two different types of technology put into one car. It's the same with atoms. So effectively, you've got your s orbitals, you've got your p orbitals, and you can kind of have somewhere in between, which we call an sp orbital. Okay, so they're just kind of, it's like petrol electric orbital. Okay, so this is called an sp orbital. Now sp comes from the s orbital, and there's a p orbital in there as well. Now the 3-bit tells you how many orbitals are involved. So we have 3 p orbitals involved and 1 s orbital, and this is where we've got one s orbital and 3 p orbitals kind of forming a brand new orbital. So it's neither petrol nor electric, it's kind of a mixture of the two. And this is exactly what we can do with orbitals. So it's not an s orbital, it's not a p orbital, it's an sp3 orbital. And it's a completely different type of orbital. Okay, but it's formed from the mixture of the other two. So hopefully you understand that, because that kind of makes it a bit clearer. Hopefully. I told you this is quite tricky, didn't I? So, if we just go back, and again, I urge you to look at topic 2 if you don't know this, but a carbon atom has in its outer shell, so its valence shell, obviously it's got a 1s orbital, it's got 2 electrons in the 1s, but we're just really looking at the outer ones because these are what are involved in bonding. So it's got a 2s2, and it's got an electron in the px orbital and an electron in the py orbital. Okay, so this is what this shows here. Okay, so you got the 2s2, 2px, and 2py. So this s orbital is full, this one here, and these ones have got 1 electron in them each. There is a pz, but that has no electrons in at all. Okay, so we can go one way and say, right, so we can form 2 CH bonds, and what we can do is these are singly occupied. Remember, that one's full, so that one can't get involved, okay, because that one's full, but these two can, and these can overlap and effectively form 2 CH bonds. Fine, okay, and that expels some energy. Obviously, it releases energy when it forms a bond, and it's minus 824 kilojoules per mole. Okay, so that's one way. So that's option 1. Option 2 is we can effectively, this is like downstairs in the bus, one of these electrons can get up, go upstairs, and occupy an unoccupied seat, which is a 2pz seat. Yep, quite fancy. And it can sit upstairs. And effectively, you now have 4 seats where there's 1 electron, or 4 kind of orbitals, should I say, stop using seats, 4 orbitals which have 1 electron in each of them. So you've got 4 singly occupied ones. There it is, okay? So now this is our setup. You have a 2s1, or 2s, should we just say, 2px, 2py, and 2pz. Now this takes energy, okay? So if you had to get up and go upstairs, you have to burn some calories. Not a lot, like, but you have to burn some calories to do that. It's the same with electrons as well. So that's going to take some energy to do that. That's plus 404 kilojoules per mole, and there we are. And that's the setup we have there, okay? So now remember, for bonding to occur, we must have singly occupied orbitals. This arrangement here, we have 4 singly occupied orbitals. Now, that means we can form 4 bonds instead of 2. Now, these 4 bonds, when you form a bond, energy is released. And the energy to form these bonds is 4 times 412. Okay, and this expels minus 1,648 kilojoules per mole. And the 4 bonds, they form this new hybrid. So these are not sp, px, py, pz. These are effectively scrapped, and we form 4 brand new orbitals called sp3 orbitals. And you have 4 of these, which is a hybrid. So it's effectively having, say, a petrol. We have an electric car here, and a petrol, and a petrol, and a petrol. Effectively, what we've done is mashed them all together and formed 4 hybrids, okay, instead. So it's got a mixture of all of them. So they're brand new orbitals. So let's look at the energy here. So forming 2 CH bonds, because that's an option, releases minus 824 kilojoules per mole. Now, forming 4 CH bonds by overlapping all of the orbitals, the new hybrid orbitals, we need to put energy in, which is not good, okay, which is plus 404, but we release 1,648 kilojoules per mole of energy when we form 4 new bonds. So the total energy change is minus 1,244. Now, it doesn't take Einstein to work it out that actually you get a much bigger energy release with doing it this way. In other words, moving an electron into a different orbital first and then forming 4 bonds than you do by just overlapping existing bonds here. Now remember, atoms are incredibly lazy. Chemistry is like the lazy science, I like to call it. Molecules want to be in a position where they're in the lowest energy form possible. And a sign where they give out a large amount of energy like this overall is a good sign as far as a molecule is concerned, because it will sit in a much lower energy kind of status than if it was here. And obviously, because this is expelling 1,244 kilojoules per mole of energy, as opposed to 824 using this one, clearly this is going to be the kind of route, or this is the kind of correct version of how carbon bonds with hydrogen to form the CH bond. And that is why carbon bonds 4 times with hydrogen. So it normally exists as CH4 rather than just CH2 because of this setup here. Okay, so really, really important. And this is because we have this ability to form an sp3 hybrid. Just to kind of point on that as well, we do form sp2 hybrids, which I'll show you in a moment, and effectively that is where you have an s orbital, merging with two p orbitals, so that's sp2. But you also have sp orbitals where you've got one s orbital and one p orbital merging to form an sp hybrid orbital. So that's all that means. So it's basically just a mixture of this bit here just says, right, we've got an S and we've got three p orbitals overlapping, and this is a brand new hybrid. Okay, this is a brand new kind of orbital. This is not an S, it's not a P, it's an sp3. It's kind of somewhere in between the two. I hope you understand that. It's quite tricky. Okay, so let's have a look. Let's kind of carry on and look at a little bit more detail. So that was a single bond, a single CH bond. You do need to be aware of sigma and pi bonds. Now, pi bonds are found in double bonds and triple bonds for that matter as well. So sigma bonds is where we have two orbitals that overlap. Okay, really important. So in the CH bond example that we've seen previously, CH4 has four sigma bonds, some with S and P characteristics, hence why we say sp3 hybrids. So the bond is effectively them four sp3 hybrids kind of overlapping, forming that single sigma bond. So another type of hybrid is where the s orbital is hybridized with two p orbitals instead of the three that we've seen in the previous slide. So we get something called an sp2 hybrid model. Okay, so effectively one of the p orbitals is not going to be involved in forming this hybrid. Okay, so we can find this example in alkenes and benzene as well. Now benzene you're going to see a lot more in year 2, so don't worry too much about it now. I'm just going to show you as an example though. Alkenes, you do need to know about that. Okay, so here we have an S. So what we can have is we can have three sp2 orbitals and a p orbital that's separate. So remember, go back to that model from topic 2. You have an s orbital, okay, which can hold 2 electrons maximum, and then you have your three p orbitals that kind of sit just above it in energy. So what we're doing here is using the s orbital still, but we're kind of merging that with only two p orbitals. Okay, and that forms what we call an sp2 orbital. So we have a spare p orbital that's left. Okay, so what we have is we have these three sp2 orbitals, and the sp2 orbitals, these three sit at 120 degrees apart from each other, and they form this planar structure. Okay, and now there's the planar structure there. Now the remaining p orbital will sit at 90 degrees. So imagine this kind of sticking out at the top here and then below like that. So you've kind of got this kind of, looks like a windmill, like a wind turbine, and you've got this bit sticking out like that, up and down. Now this one sticking up and down is your traditional p orbital that hasn't been hybridized. And the remaining S and the other two p orbitals have merged to form this new hybrid, which is an sp2. And these three orbitals kind of sit in a nice kind of triangle shape like this. Okay. So in alkenes, a pair of sp2 orbitals, so these two, there's one there as an example. You might have another molecule somewhere over here. So imagine you've got two of these side by side. These two orbitals, so this one and a neighboring molecule, can merge together to form a sigma bond. And what that does, it helps to pull the molecules a little bit closer together. And then that allows a creation of a pi bond. Okay, so let's have a look at the diagram. So here we have an s orbital. Okay, so your S is the kind of, imagine these as, it's quite difficult to show, but imagine this and another molecule over here. They kind of overlap, the orbitals overlap, and we form this sigma bond here. What you do have though, remember you've got this kind of pi bond that's kind of, pi bond, the p orbital that's kind of on the top here, kind of 90 degrees to it. That then starts to overlap with a neighboring molecule. So you've got this kind of the p bond, so the p orbital here, and you've got another molecule near it. And effectively, these kind of vertical ones here, they align up top and bottom. Okay, so this is not a hybrid version. And what these do is these overlap to form this. Okay, so this is your pi bond. Okay, and so there's your sigma there. This might kind of make it a bit easier. So you've got your sigma, so that's your carbon there. That's your sigma bond. These overlap, and you've got these two p orbitals that kind of on the top and bottom on each of them, and they kind of merge together. They kind of mix, and they form this pi bond here, and that is a double bond. So it looks a bit like a hot dog and a bun to an extent. So your hot dog's like the sigma, and the bun bits, you've got two bits of it, which is the pi bit there. Okay, so that is effectively what a pi orbital is. I hope you understand that bit. Okay, so just go back. It is quite tricky. If you're not sure, go back and revisit and have a look. So just to kind of look at, make it a little bit more clearer. Again, I'm throwing a lot of diagrams here just to kind of show you what these look like. Hopefully it'll just reinforce it. This is an example of 6 carbon atoms bonded together. Again, you'll see a lot more of this benzene. You'll see more of this in year 2. If you're not doing year 2, you don't need to be too concerned over it, but it's really just to try and kind of show you what's happening. So you've got your 6 carbon atoms here, and they're all kind of joined up in a ring. These red circles here are hydrogen. Okay, so you've got your sp2 hybrids kind of bonding here, here, and here. So they're your sp2s. Okay, so that's your trigonal bit there. You're kind of playing a bit. And then you've got this p orbital that wasn't involved in the hybrid, kind of top and bottom. Okay, and you've got that with each of your carbon atoms along there. Now, in this orbital here, you've got an electron that's kind of whizzing around in this figure of 8 here. The other electron's involved in bonding. Now, what happens with this, effectively, these are just single bonds, is these electrons can overlap. I know it doesn't look like it in the diagram because it's for diagrammatic purposes, just showing you kind of what it looks like. But these are close enough to overlap with each other, top and bottom, like that. And effectively, within benzene, they kind of merge together and form this kind of like a donut shape, I suppose. And in this case, in benzene's case, it's quite unique. And again, you don't need to be too concerned about this in year 1, but they will merge together and form this. And what it's trying to demonstrate here is that orbitals overlap to form bonds, and this is effectively a bit like a pi bond. Okay, so let's kind of move away from that bit. Okay, so that's the trickiest bit, so breathe. Okay, so let's look at some of the bare areas as well, which is electronegativity. So electronegativity happens in covalent bonds as well, so there's a lot of stuff in covalent bonds here. So electronegativity is the ability for an atom to attract electrons towards itself in a covalent bond. So this happens in covalent bonds only, okay? So the further up and right you go in the periodic table, excluding the noble gases, so they've got a big black line through them, the more electronegative an element is. So in this case, fluorine is the most electronegative element in the periodic table. And you can use this scale, which is called a Pauling scale, quite a useful scale, quite straightforward, and it basically tells us how to quantify how electronegative an element is. So the bigger the number, the more electronegative it is. So fluorine is the most electronegative element in the periodic table, and so therefore has a electronegativity value of 4. And you can see some of these elements, like oxygen, for example, is not quite as electronegative. Chlorine is less electronegative still. Nitrogen, carbon, hydrogen, etc. So these are the values that we give to them. Now, essentially, the bigger the difference in the electronegativity value, the more ionic a compound will be. Okay, so if we've got, basically, if you've got sodium, which is, say, at one end here, and chlorine, which is at the other, clearly one's very electronegative and the other one isn't. Now, we know that sodium chloride is ionic because, you know, the difference in electronegativity is so big. But if we look at something, say, such as carbon and hydrogen, which is, you can see is 2.2 and 2.6, the difference in electronegativity between them two is not as great. So they're more likely to be covalent. And obviously anything which has no difference in electronegativity will be purely covalent. So there'll be no ionic characteristics already. And in reality, molecules have some covalent characteristics and some ionic characteristics. Some are more purely ionic than others, though. So in reality there is a mixture of some of them there, but we can kind of categorize, broadly speaking, molecules which are generally seen as covalent, and molecules which are seen as ionic. Okay, so let's look at some of these in a little bit more detail. Let's look at some polar bonds. So covalent bonds can become polar if the atoms attached to it, spit it out, have a difference in electronegativity. So, for example, the bigger the difference in electronegativity, the more polar a bond will be, as we've seen before. So let's look at an example here. This is HCl. Now, Cl, as you've seen before, is more electronegative than hydrogen. And what it does is, remember when we looked at the sharing of electrons between these atoms, is it pulls these electrons towards itself because it's a lot more electronegative. And you get this polarization, this polar bond. And we put these little symbols here. This is a small delta. So delta positive for hydrogen, because effectively the electrons it was sharing is being kind of moved over towards chlorine, and delta negative for chlorine here. So the electrons are being moved across to one side, and effectively we have a little dipole. We have a little positive charge here and a little negative charge here. Now this is not ionic. This is still covalent because the electrons are still shared, but it has a mini kind of polarity within the molecule itself. So, like I say, to show that, we put these little delta positives and delta negatives next to it. But atoms with the same or similar electronegativity values are not polar, so they're non-polar, and the electrons kind of sit bang in the middle, so they're nicely shared. And hydrocarbons are classed as non-polar, so things like methane, butane, ethane, etc. You'll see that later in the introduction to AS. Organic chemistry topic later on, so hydrocarbons are basically non-polar. You've also got some as well, such as molecules which probably have more than one atom in there. So, for example, water. So if you've got an uneven distribution of charge, this leads to polar molecules as well. So water is a classic example of a molecule that is polar. So the electrons, as you can see here, are being pulled towards oxygen, which is more electronegative than hydrogen. So you get two sets of polarities. You've got one here and one here. Okay, and it's this property that helps water dissolve, or helps to break up ionic compounds, because of this charge here. It kind of muscles its way into the kind of giant ionic structures and breaks them up, and that's why you get ionic compounds that are generally soluble. You've got other ones as well. You've got to be a little bit careful with these. You've got carbon dioxide. On the face of it, might look polar because you've got an oxygen and a carbon, and there is an electronegativity difference between the two. However, what you have here is symmetry. So you've got one end pulling electrons to one end, and the other one's pulling it equally, but in the opposite direction, on the opposite side. So molecules like, for example, carbon dioxide, they're classed as non-polar. I know we have polar bonds, we have polarity here, but when we look at the molecule as a whole, there is symmetry there. So basically, you've got two ends of this molecule which have got the electrons, and the middle bit is kind of left exposed in the middle with very little electrons. So this is what we call a non-polar molecule. So just be really cautious with that. Okay, so let's look at some intermolecular forces, and then what we'll do is look at some metallic bonding, and then that'll be it. Okay, so it's quite a bit in this topic, isn't it? So. Right, so we talked a lot about bonds before. So bonds are these attractions between atoms. They're quite strong, okay? Now, intermolecular, as the name suggests, is inter means between, and molecular is molecules. So this is forces between molecules. So all the other bits we've been looking at before, these are bonds between atoms or ions. So it's a very different thing. Don't get these forces mixed up with bonds, okay? Now, there's three types of intermolecular force. Okay, one of them is van der Waals, which is Dutch, I believe he's Dutch. So van der Waals, or also known as induced dipole-dipole. You've also got permanent dipoles, and you've got hydrogen bonding as well. So you've got three types of intermolecular force. Now, all of these forces are weaker than bonds. Okay, so bonds are very strong, and they're really difficult to break down. Forces are weaker than bonds. Okay, so kind of categorize them into two containers. One is bonds, and one is forces. Okay, so look at the first one, which is van der Waals. Now, van der Waals are the weakest type of force that exists between molecules. So you need to know the criteria for these as well. How do we know which force exists where? So any molecule or atom with electrons can form a dipole. Okay, as we've kind of seen in the earlier example, some of them dipoles can be permanent if they exist. Some of them, can be induced if they come near another molecule. So van der Waals, if they've got electrons in there, basically, it can be induced. So this occurs. So for example, chlorine. So chlorine's got no kind of there's no dipole in chlorine. Both elements are as electronegative as each other. However, we can induce a dipole, so we can bring about a dipole. And this is a temporary dipole. And this can happen when you've got chlorine molecule floating around in a container and it comes into contact with, say, another chlorine molecule, for example. And these have electrons in them. Now, when the electrons in this chlorine comes into contact with electrons in another chlorine molecule, we get the electrons in the bond moving away because they kind of repel. And for that moment in time, we have this polarity. So you have this kind of temporary kind of positive, delta positive on one side, and temporary delta negative on the other side. And this is because you might have another chlorine molecule here that's kind of nudging the electrons in the molecule to one side. And this is why we call it a temporary dipole. Now, this only exists, like I say, when you've got two molecules or atoms nearby. And when they move away, when they kind of drift apart, the interaction is destroyed. Okay, and as long as that interaction is there, you might have neighbouring molecules that will have this polarity as well, this temporary polarity, and you have opposites attracting on these two ends of the molecule here. And so this is a very weak force because it only exists if this molecule is nearby. But this is a van der Waals. This is a very weak force between molecules, and this is obviously your delta negative and delta positive, and this is a van der Waals force. So this happens in any molecule that has electrons, and obviously can form this temporary dipole. Okay, so the next type, so if we go kind of a little bit higher in strength here, these are called permanent dipole forces. Okay, now the word permanent kind of gives you a bit of a hint here, doesn't it? So the van der Waals were dipoles, but they were temporary, so they only existed when another molecule kind of came near another one, so two molecules coming together. Permanent dipoles basically means that the molecule itself has a dipole, irrespective whether it's near another molecule or not, i.e. it's a permanent one. So a classic example here is HCl, as you can see, obviously, in this diagram here. So, when you have HCl, you have this permanent dipole here, delta negative, delta positive. Chlorine is the most electronegative element. And you have these electrostatic forces between the delta negative chlorine and the delta positive hydrogen between them. So the delta negative part on one molecule is attracted to the delta positive on the other one, as you can see on there. And unlike van der Waals forces, dipole-dipole interactions, or your permanent ones, are stronger. Okay, because they're permanent. There's no, they don't exist because they're near each other. So, really important though, molecules such as HCl, for example, they do have permanent dipole-dipole forces, but they also do have van der Waals. They don't have one or the other. These ones will have both. Okay, so permanent dipole-dipole and van der Waals. Really, really important that you know that. So a classic example of something, for example, with a permanent dipole is water. It also has hydrogen bonding, which I'll come into in a moment. But in this example, you can try this at home, really. If you take a ruler and rub a duster on it to basically create a charge on the duster, and if you have a trickle of water, just a trickle coming out of your tap, and move the kind of the kind of ruler, the plastic ruler, to the water stream, you'll see the water will kind of bend slightly, and that's because water is polarized, and you've got a rod which has got positive charges on it, and what will happen is the negative bit of the water molecule will be attracted towards the positive rod that you put near it, and so you'll see this trickle. So there we are. So try that one. And the last type of intermolecular force is hydrogen bonding. Now, hydrogen bonding is obviously, it's got the word bond in there. Don't get that confused with ionic, covalent, and metallic bonding. Okay, hydrogen bonding is still a force. It's a weak intermolecular force. Now, hydrogen bonding is the strongest out of the three forces, as you can see on there. And water is an example of a molecule that will hydrogen bond. And this is why. So, hydrogen bonding occurs when you have an interaction between hydrogen, as the name suggests, and three of the most electronegative elements in the periodic table. And in this case, it's nitrogen, oxygen, and fluorine. So if you have any of that combination there, if you have a combination, we've got a hydrogen and another molecule has a nitrogen, oxygen, or fluorine on there, then you will have hydrogen bonding between the molecules. So here's an example. So there we are. So you've got oxygen on one water molecule with hydrogen on another. They will be hydrogen bonding. Obviously, we represent hydrogen bonding by drawing a dotted line. And it goes between the delta negatives and the delta positives. And it must be between the lone pairs. Okay, really, really important. Lone pair of electrons on the oxygen. So, and just like we mentioned before, hydrogen bonding, any molecules which have hydrogen bonding will also have van der Waals forces, and they'll also have permanent dipole-dipole interactions as well. So water has all three intermolecular forces between the molecules. Okay. Right, so again, don't get them confused. These are intermolecular forces. They're very different to covalent, ionic, and the last example we're going to come on to here is metallic bonding. They're kind of two different pots. Okay, so let's look at metallic bonding then. So metallic bonding is obviously a type of bonding. It happens between metals, as you would probably expect. They have giant metallic structures. So what you need to be aware of is what that structure looks like and what the properties are for metallic bonding. So positive metal ions are formed as metals donate electrons, and they form this sea of delocalized electrons that kind of float around in the structure. Okay, so if you had to look at metal, that's what it would look like. Now, you have electrostatic attractions, there's that word again, between your positive metal ions and your delocalized electrons, which are negative. So you've got this attractive force between it. And the more electrons an atom can donate to the delocalized system, the higher the melting point. Okay, so obviously you have stronger attractive forces between the positive metals and the negative electrons if you've got more of them. So magnesium, just to give you an example, so magnesium has a higher melting point than sodium because magnesium can donate 2 electrons, which is group 2, whereas sodium only donates 1 per atom. So sodium's quite soft, you can cut it with a knife, it's not very hard at all. Whereas magnesium, you might have seen it, it's like magnesium ribbon, you put it in a Bunsen flame and it goes really bright white light. Metals, they're really good thermal conductors as well, so obviously they're good for pans and cooking things, and that's because the delocalized electrons can transfer the kinetic energy. Remember, if you do physics, you'll know that if you transfer heat through conduction, it's the electrons that kind of bump into each other and pass that energy along. Metals are obviously no surprise. They're generally good electrical conductors, again, because of that delocalized electron system that they have there. Very similar to ions, so giant ionic compounds where they have delocalized ions. They don't have delocalized electrons, but they have delocalized ions. Then delocalized electrons will also do the job as well in terms of conduction of electricity. Hence why graphite will conduct electricity, because it has the delocalized electrons there between the layers. Metals, they have high melting points because of these strong electrostatic attractions. And obviously solid metals are insoluble. The bond between the positive metal ion and the delocalized sea of electrons is far too strong to break, and so therefore water can't actually break into that. And metals are also malleable, and they're ductile as the ion layers. Obviously, these can slide around. You can see they're in a kind of nice, neat layer. These can kind of slide around. So if we take a hammer to this on this side and hammer it on that side, then these layers can kind of slide over each other. But the delocalized electrons kind of shift to kind of merge and try and keep it all kind of held together nicely as well. So obviously you can hammer metals into shape as well, which is quite a useful property. Okay, and so just kind of moving on to the final slide, I suppose. This is just summarizing everything that we've seen here, because there's an awful lot here. Now, remember, this is looking at bonding. There are them intermolecular forces as well, but deliberately the forces are not on here because I don't want to kind of confuse you. So looking at the bond types then, so you've got 4 main types of bonding. You've got giant covalent, which are known as macromoleculars. So these are graphite, diamonds, and silicon dioxide. Obviously, they're normally solid. They don't conduct electricity, apart from graphite. They don't conduct electricity as a liquid either. There's no ions moving there. They're not soluble in water, and they've really high melting points. Simple moleculars, so these are your simple covalent structures like water and ammonia, for example, and iodine is another one. So these are generally how liquid and gas at room temperature and pressure. Iodines are solid, it's a bit of an exception. They don't conduct electricity as a solid nor as a liquid. They're not really massively soluble, but it depends on the polarity of the molecule, as mentioned before. And they have low melting and boiling points. They're not giant structures like graphite or diamond. Ionic compounds, obviously, are giant ionic. They are giant by nature. So they are definitely solid at room temperature. They don't conduct electricity when they're solid, but they do when they're a liquid because the ions are free to move around. They are soluble in water because of the ions. Water can get in between the ion structure and break it up. And they have high melting and boiling points because of the strong electrostatic forces between these oppositely charged ions. And the final one is obviously metallic bonding. As we've just seen there before, they are solid. They do conduct electricity because they have them delocalized sea of electrons. They conduct electricity as a liquid as well for the same reason. They aren't soluble in water, and they have really high melting and boiling points because of their strong electrostatic forces. So, and that, there we are. And your polar molecules, just to kind of chuck one last bit in there, your polar molecules dissolve well in polar solvents like water, so that's really important as well. So for example, ammonia will dissolve well in water, hydrocarbons don't. So if you take a classic example is cooking oil, for example. Cooking oil is a hydrocarbon. If you put cooking oil in water, it won't mix because they're immiscible, and that's because hydrocarbons are not polar. And generally, for things to dissolve, you need polar and polar to dissolve. Okay. And that is it. So that is chemical bonding. Just as a summary, make sure you know you've got your covalents, your ionics, and metallic bonding. Make sure you understand about hybridization and what actually happens in covalent bonds. Make sure you understand about your electronegativities and your 3 different types of intermolecular forces, which are van der Waals, your permanent dipole-dipoles, and your hydrogen bonding. And that is it. Like I say, these are available to purchase from the test shop. Have a good look around if you wish. The link is in the description box below. But that's it. Bye-bye.